Okay, so this is a slightly weird video for at least two reasons. Um, the main one being that I'm making it because I was very unsatisfied with how day 15 went. Um, I didn't understand why Eric was giving us a problem that was clearly nothing but a fairly general shortest path algorithm. Because first of all, there's nothing interesting about that. If you have a shortest path in your library, you just apply it to that, and the weight and neighbor functions are the only things that you need to plug into a shortest path algorithm to get it there. And those were both, a minute or two to write. I mean, modulo the fact that I'm terrible at writing a neighbors function, even for Manhattan neighbors. Now that I've done it 3 times, I think, in this competition, I think I could get that in a minute, finding the 4 neighbors, right? And the weight function is just looking the position up in the grid. So if you have a general purpose shortest path algorithm, it's an utterly trivial problem which holds no interest whatsoever. And if you don't have a shortest path algorithm, writing one, I actually don't think that's appropriate for a programming competition, because if you want to do it algorithmically efficiently, you need to build quite a sophisticated data structure, like a Fibonacci heap, which I did for fun a couple of weeks ago, but again, that's just for fun, and I've never used one in earnest, because you generally don't need fancy data structures for things. And so I was annoyed at the problem, and I was annoyed at my solution. And last night, just as I was going to bed, I realized, well, you know what, we probably actually could have done that just with breadth first search. And so that's what I would like to attempt now. I should say the other slight complication to this video, I'm up in the mountains and we've lost power. So I'm, on battery on the laptop. So that's why things look quite different. Anyway, let's look at how we can do. So these were our solutions. Oh, sorry, I need to switch to my other scene. Sorry if this ruins the mystery for you. So let's code this. You know what? I think I might actually have to close my shades because it's very glary up here. Okay. Now I think I can see a bit. Oh, what was that? No. Now I think I can see a bit better. Okay, so I think we got that part right. I think because we're going to need to use a queue, I think. So, data equals lines digit grid of lines. I think this is more or less exactly what we did last night. Oh, of course. Oh, that sounds like power coming back on. Good for us. Yes, okay. So, we have our digit grid, right? Now, my plan for doing this breadth first search is, what if we considered that every time you moved, you fell into a hole and needed to climb out of it, right? So we're going to use 3-dimensional coordinates to do that. So, and then what we need, all we need to do a breadth first search is a neighbors algorithm, right? So the neighbors of a 0.3 so here is the trick. if p z. So if our height is below the is lower than the hole we need to climb out of, right? Grid py px. Then what's adjacent to that? All we do is climb in that case. X, y, z, p, z plus 1, right? So if we fall into a hole, we climb up until we're at the top of the hole. But once we're at the top of the hole, then we just do our regular old neighbors. So, no, we need to create our array. Right, so that's why that's a neighbor. But we always move to, we always start at height 1, right? Yeah. Now we just have 4 of those, right? I made 5, so we're going to have to change that. Y minus 1. If x is less than grid count. And we know that the grid is square, so we don't really have to double index this to get the count, even though that in some ways would be a little bit cleaner. If it is less than grid count minus 1, right? Plus 1. Plus 1. And okay, so first let's just see if that compiles. Oh, and of course it doesn't. What did we not get? PYY. Oop. P dot. Return, and this needs to be a 1-element array. Okay, so that looks good to me. Now, ba-ba-da-ba-da. Now I guess we just do, I'm getting all these messages about my power coming back on. So, so we're a queue of 0.3s, right? And we're going to say, and this is a little bit clever as well, we're going to start, because, you know, we realized quite late in the process that we shouldn't count the first thing. We're going to start at the top of the first hole, right? Because the 0, 0 number, I don't even know why there is a number there. It's irrelevant, right? So, but we are going to have a problem with the bottom right in this case. So, should have made it a variable or something, but it's fine. Okay. So now we just do our breadth first search. In neighbors. Where should we actually do this? Let's do this here. In fact, since we're not really going for time, let's use the v. So if this is the first time we visited, then we push n. Right? Okay, so that is a breadth first search. It doesn't actually generate us any of the information we want, though. So what we really want is, you know what? Instead of just this visited thing, we're gonna, this needs to be a var. We're gonna say that this is from point 3s to how long a path it is to get there, right? In fact, can we just make it a zero? Does that work? And then we say if D's, so our clever stuff is not necessary. If D's of n is equal to nil, then D's of n equals D's of p, that's its predecessor. We need to bang that, but we know it's going to be there. So how are we doing on compilation? It compiles. Oh, and it runs in theory. So print D's of x 99, y 99, z1. We're going to have to special case, based on how we've written this, we're going to have to special case the thing actually related. Oh, and that's not the print. The risk factor or the depth of the hole of the final grid location. What explicitly cast to any? What? D's. Oh, because it's an optional, but we know it's there, don't we? 402, and then what we need, and that gave us the 1. So how do we special case that? We we've said we've gotten to the 1 there, get to the 9. So actually, if we just make this, because we will have climbed the hole, because we've set it to neighbor, so that is grid of 99. 99. And that's the right answer. So, and it ran very quickly. So you can just breadth first search using this kind of hole climbing approach. And the reason this hole climbing approach is, first of all, it wouldn't work if there were negative numbers in there, but you could have accommodated by negative numbers by just seeing what the minimum was and adding, a large number to everything, and then kind of subtracting that off at the end of the day, to make all the holes positive. Similarly, but it needs to be a small range of numbers that you're going over. The point here is that we only have 0 through 9, so at most we're multiplying the number of nodes in this grid by a factor of 10, right? And that is, perfectly, we can actually time this because it's more or less instantaneous, right? Yeah, it's more or less instantaneous. Just getting all the Swift machinery up is what takes all the time here. So I suppose the next thing, so that's actually part 1. So let's copy that to. So now, with this much larger grid, our algorithm is still good. We could do the exact same thing we did last time in terms of just manually recreating this grid thing here, right? But that's a bit dull. So, let's say, when do we ever look at the grid? We only look at it here, here, and these are easy to fix because we know we're just 5 times as large. Right? There. But grid 0, 0 is all the same, and then, we're going to have to change that last line to get the bigger thing. This is what we need to do. So let's see. If PZ... So now we're going to mathematically compute the... Well, you know what? Let's put it in a separate function. Again, we're not going for time or concision. So, value of x, y, and we need to capitalize, don't we? Okay, so now we're not confused by any other syntax that's hanging around. So, we say it is x percent plus x over grid count, right? That's our new x. What? No, I'm confusing things. So the position in our grid we're looking at is just modulo the count, right? So grid y percent grid count and x percent grid count. Okay, so that's our base value. And then we want to add on the x over grid count, y over, because every time we duplicate the grid, and it fits in 80 characters, and that's what really matters. So we can just replace this with, with val of px, py, right? Something didn't work. Plus over grid count. Oh, was that it? Just, you're not allowed to, you need to put spaces after things? So, that was substantially slower. It got us to 403. It computed, I'm looking over at the camera, which is no longer over there. So, we just haven't modified our last one, but that's how long it took. How long did it take? 2.5 seconds to compute all this. So breadth first search is still easily good enough. So, it's $24.99, isn't it? In both cases. And grid 99. And so what was our math here? Plus 4 plus 4, right? So 1,000, 2 1,000, 3 1,000. And that, oh, it crashed. That's not ideal. 20. So even with the benefit of thinking it through, we're not. Line 41. Grid 99. These need to be changed as well. And that was just crazy. Oh no, that wasn't crazy. Plus 4 plus 4. But that's the value of it. It gets 1, 2, 3, 0 plus 1, 2, 3, 4. Well, that seems right to me. But for now, let's just see if that works. DS.3, yeah. Okay. So we still have to do a little bit of debugging, apparently. 1, 1,000, 2, 1,000, 3, 1,000. It's just our last line. What is the problem here? Times 5. Wait, 100. I'm an idiot. That's the short answer. It's 2,500 points total. Not 2,500 in each direction. So 5818, what is, I don't recall what 2 Fibonacci heap was. And look, the Fibonacci heap is actually substantially slower than doing breadth first search, which is kind of a lesson about fancy data structures. 2844. Ooh, so not even close. $28.44. Let's actually write that down. So, okay. So we're getting the wrong answer here. Why is that? Over grid count. Y over grid count. just 5 over 2. 5 over 2 is 2. Yeah, that makes sense. How about 1 over 2 is 0? Yeah. So I think our valuation, I thought our valuation function was right here. Plus 1y plus 1 z1. Oh, of course. Okay. We forgot that this is all modulo, right? So it's nu v modulo 9 plus 1, right? It's actually nu v plus 1. Is it? Because if you have a 1, then you want to get it to a... Yes, it's... Sorry. Yes. No, that's not right. Sorry. So if you have a 1, you want it to remain if you have a 9, you want it to remain a 9. So you turn it into 10 and then you modulo it 9, right? Yes, but what turns into a 0? 9 turns into a 0. This is the easiest part of the whole thing, and I think I did it effortlessly last night, didn't I? So the point is, we've added things to it, and then we want to modulo them by... So if we want to take 1 to 9 and go to 1 to 9, we subtract 1, then we modulo it by 9. This wasn't quite the same math we did before, and then we add 1 to the modulus. Okay, that makes more sense, I think. 1 1000, 2 1003, and that gets us, and that crashes because nu v minus 1 modulo 9 plus 1. So where am I failing? Nil on line 42. Nope, still doing something stupid. Come on. Where does it start? Index out of range. Oh, plus 4 plus 4. No. Really? So, what is this? Well, unwrapping on 42. I don't know what's going on here. We're not looping over these things. Word count times 5 is 500. Oh. Oh, no. That's... because we're looking for neighbors. We count 5 minus 1. That's good. So we'll be up to grid count. Yeah, let's... And this is going to be a lot of stuff. It's going to be 2,500 points, isn't it? But we can at least see what points are ending up in there. Two, 378, 446. This is all looking pretty reasonable. V is less than val. Z, and the Z's are never terribly big, which looks right. Well, let's... What are we exploring? So a bit of a rocky end to this re-implementation with all this crap, you know? 499 Z9. Oh, did we just do it again? We didn't... That's what we did. Because we have to do the same logic here. 99 plus 4 plus 4 minus 1% 9 plus 1, and we need another parenthesis. So, yeah, just a bunch of picky things. So 2840 and 2844. So 2840 was the right answer. 2844 was including the initial thing. So, how long did that? That's still... Actually, I have no idea how long it took us because my clocks aren't synchronized anymore. Maybe OBS will tell me how long it took me. I'll have to watch the video. At the very least, I'm much happier. We can actually switch to this. I'm much happier with this breadth first search solution, and it restores my faith that Eric would not give us a problem that requires some incredibly overpowered algorithm. So, anyway, I've spent far too much time worrying about day 15. So, join me tonight when I see how I do on day 16. Hopefully better than I did on day 15 the first time around. See you then.